okay? It looks, well, okay. Yep, well, we'll see in a minute. Nope, something's going on with the, okay. Oh, I think you've got, okay. Does this work? Oh yeah, it does. Right, I think I will try not to keep you too long for your tea break. So I've got 25 minutes, I believe. Is that correct?
You can have 30.
I can have 30. Okay, there. I've been asked to talk about rogue waves. My name is Meric Srokosz. I'm a professor of physical oceanography in Southampton. This is work by my PhD student, Alex Catterall. It's all published, so if you want to read the details, you can go away and read all the gory details. I am not going to give you the gory details. This is a very high-level overview. My co-supervisors were Ben Mote and Bob Marsh. So we're at the National Oceanography Centre, University of Southampton, and this was sponsored by Lloyd's Register Foundation. Lloyd's Register, an insurance company for ships, and they're obviously concerned about big waves sinking their ships. So what is a rogue wave and why do we care? So in simple terms, it's an unexpectedly large wave given existing wave conditions, and I'll give you some examples of that in a minute. It's been known of anecdotally. I mean, I had a colleague working on waves in the 1970s who talked to lots of sailors, and they all talk about these huge waves unexpectedly just appearing out of nowhere, or big holes in the ocean and destroying ships. And there's a, which is the pointer, there we are. There's these sort of compilations, this particular compilation from Carriff and Penlovsky of large super tankers, I think, that have sunk, or super carriers actually. I'm not going to discuss the theories of rogue waves. I think you've been doing that for the last however many weeks. There are lots of publications, lab experiments, theory, modeling, real world observations. I'm going to focus on real world observations because that's actually the most difficult thing to do. I'm going to go with the standard definition from Dista's review of the height of the wave is bigger than twice HS, or the crest height is bigger than 1.25 HS. I'll define what HS is, significant wave height, in a minute. So the first real observation of a rogue wave was from the Draupner platform in the North Sea. It's North Sea oil platform on the 1st of January. It's also known as the New Year's Day wave. You can see the background trace. This is time. You can see the sort of background waves are not that big. And then this big wave came out of nowhere and hit the platform and caused some damage. Well, this is the first instrumental measurement. They had a downward pointing sensor. I think it was a laser, but it might have been a radar sensor. I think it's a laser. And they were able to measure it. So this was the first clear measurement in the ocean of a rogue wave. And it's had a crest height of 18.6 meters and a wave height. We use zero crossing wave height. So that basically means we measure from the trough to the crest, where it crosses the zero line. That means we can ignore little small waves, which are not really of any interest to mariners or oil platform operators. And the significant wave height, which I will define exactly in a little while, was 12 meters. So the crest height was 1.55 times HS, and the height of the wave was 2.13 HS, exceeding those criteria for rogue waves. So this was the first real open ocean measurement of a rogue wave. I should say that I was reading my newspaper on the 3rd of December, and there was a little article, rogue wave kills cruise passenger. An American woman was killed and 4 passengers injured when a massive wave struck the Viking Polaris cruise ship while it was sailing towards the port of, I can't pronounce that, in southern Argentina. On an Antarctic cruise, a 60-year-old woman was hit by broken glass when what the Viking called a rogue wave incident happened. 4 of the passengers were injured. So these things do happen to ships and do cause, I mean, if people are being killed, I mean, not just this one person, but ships have disappeared and so on. So it's a really big issue in the marine industry. So the aims of the study we wanted to do was there have been lots of observations, but we wanted to try and put together as big a data set as possible, because the current sort of statistics is that about 1 in 10,000 waves is a rogue. So if you want to study rogue waves, you need a lot of wave data, because 1 in 10,000 is not a common occurrence. So the questions we were sort of asking, because these are practical questions, can the probability of rogue wave occurrence be characterized by sea state parameters available from wave models or satellite observations? So in other words, the sort of standard observations that go on for oceanography, can they help characterize rogue waves? How spatially variable, and when I say spatially variable, I mean location variable. If I'm in the North Atlantic, is that different from the North Pacific? If I'm on the Southern Ocean, does it matter? And the final question is, given climate change is a big issue, is the probability of rogue wave occurrence changing? And then the last question, which we were going to look at, was can machine learning help, which we did look at, and the answer to that is no. And the reason for that is very simple. We have an unbalanced data set. We have a 1 in 10,000. So although we've got a lot of measurements, which I'll explain in a minute, there's not enough rogue waves as a percentage of the total measurements to come up with a good machine learning solution. We tried various tricks to try and unbalance the data sets. There's various clever things you can do, but it turned out that none of them really worked, and we didn't really get anywhere with that. So that's not published. The other things I'll talk about are all published. So I just want to talk a bit about wave measurements. There's various measurements. There's marine radars on the left. Sorry, left, yeah, your left, my. Fixed sensors on platforms. These are usually either radar or laser sensors, and then there's buoys. And all sorts of pros and cons. The trouble with marine radars is that they're proprietary, and they won't tell you how they get wave height out of them. There's some issues about that, so you're never quite sure whether you're really measuring the wave height. You can clearly see the wavelength structure from the motion from the radar, but the wave height is difficult to get a handle on. Laser and radar sensors are great, except they're affected by anything that's between the wave and the sensor. So if you've got spray, braking, anything like that, you may get a mismeasurement. Wave buoys, they also have problems. There's two types, well, there's more than two types, but there's small wave buoys, which is the ones I should be using data from in this talk, which are about 1 meter, so they're quite small. But there are also some very big wave buoys, 3 meters, and even bigger ones up to 6 meters. Obviously, these ones may not correctly capture the motion of the waves because they're moored and they're also big. This one, you hope, will follow the wave quite well and get you good measurement. But even here, you've got a problem. If you had long crested waves, the buoy would have to go over the top of the wave. If you've got short crested waves, so they're more like a hillock, it can go around the side. It won't necessarily go over the top, so you're probably going to underestimate your height. You've got a mooring system. So if the wave's really big, it's possible that the buoy will just be dragged through the middle of the wave because the mooring can't go and give you enough slack to get you over the top of the wave. So there are all sorts of problems with all these. So we have imperfect measurements. Unlike in the laboratory or in theoretical models, you've got problems. You can get satellite measurements. Things I've worked on is measuring significant wave height and zero upcrossing period using altimeters. This is just from a single satellite. You can still see the tracking of the satellite tracks in there. Now we've got multiple satellites, it's less tracky. So you can get that sort of measurement from space. This is Southern Hemisphere winter, so that's where you've got big waves in the Southern Hemisphere and not much in the way of waves in the Northern Hemisphere, and longer waves in the Southern Hemisphere and shorter waves in the Northern Hemisphere. There's a new satellite, CFO-SAT, which stands for Chinese French Ocean Satellite, I think, with an instrument on it which has got a rotating scan, which scans over about 180 kilometers, and you can get wave spectra. So this is giving the wavelength and direction. So the satellite's traveling this way, the wind is blowing that way. You have 180-degree ambiguity because you're sampling the surface in one scan. You don't know which way the waves are going. You can't distinguish the direction of travel just from that. So there are problems with that as well. Well, these are the sorts of measurements we have. Computer models of waves are generally spectral models. They produce spectra like this. So this is from a computer model showing you where the main storm system is. There are two systems in here. There's a smaller one and a major one. This is a 1D spectrum. This is a famous John Swap spectrum showing us this was measured offshore. So as the wind blows offshore, energy travels to longer and longer wavelengths, higher frequencies. So this is all the maths you're going to get. We usually work with wave spectra, frequency and direction, or wavelength and direction. In this case, because it's a wave buoy, we're just measuring in time. So working with a 1D spectrum, we have integrals of the spectrum which become important. The significant wave height is basically 4 times the variance, standard deviation of the sea surface, the elevation. There's a zero upcrossing period, which you can define statistically, and a mean wave period. And often we also use the peak frequency, which is what the frequency is at the peak of the spectrum and the associated period. So those are standard spectral parameters that we use in waves. So we decided to use data well wave rider buoys for two reasons. One is that they're small, so they should be less affected by some of the other factors that affect the big buoys. Also, although they've changed over time, the basic size of the buoys, the 1 meter size of the buoy has not changed, and the weight of the buoy has not changed. So basically, physically, they are, even though the electronics and things have been upgraded, the buoys have basically remained constant over all the period of observations. That reduced the number of wave observations we had to 80 records from wave riders that were out for varying lengths of time. I can't remember, I don't know, I put on the dates here, it's in the paper, over what period these observations were collected. But we had about 1.25 billion waves. We quality controlled them to get rid of any things that we weren't happy about. We analyzed them in terms of Cs. In typical wave analysis, you take 20 minutes of data of wave elevation, calculate a spectrum from which you can get the significant wave height and the zero up crossing period and other parameters of interest. So we analyze them in those, that gives us our HS. And then we look in each of those Cs to see whether we have a rogue wave, either with the crest height bigger than 1.25 or the rogue wave height bigger than 2 HS. So we have about 263,000 rogue waves. We did two studies which are published. One is Geophysical Research, Journal of Geophysical Research Oceans, and the other in Nature Science Reports. This one was all about trying to work out whether you could say anything about rogue waves given standard parameters. And this one was all about, are there any trends in the data? So this is where the buoys are located. The color coding gives you the depth. The shallowest depth is about 10 meters, but they're up depths of over 200 meters, some of them. One point to note is that this is all in the northern hemisphere. We have no southern hemisphere observations. There's a lack of southern hemisphere observations. Actually, where most of the big waves are is around the south, around the Antarctic. And very few open ocean. Most of them are coastal, as you can see, around the west and east coast of the States, a few around Hawaii and one or two other islands. So the data set is far from perfect for what we'd like to do, but this is what we've got to work with. So simplest thing is we will just plot significant wave height, maximum wave height, that's the crest height. And these lines are, this will be crest height, sorry, this is maximum wave height. So this is rogue wave height, say twice HS will be this line, 3 times, 4 times, 5 times, and similarly for the crest height. And this is just a distribution of those points. As you can see, there's no obvious way to say that H bigger than HS over 2, bigger H over HS over greater than 2 is necessarily a rogue wave. You can't distinguish the distributions by some simple criteria. Rogue waves do not seem to be easily characterized by HS. We did the same for joint HS. This time we're using peak period. And again, you plot the distributions and you can't distinguish the rogue Cs from the non-rogue Cs using these simple parameters that are commonly used by mariners and people working at sea. There's a double peak here in this marginal distribution of period. I'll come back to that later. But you can't make any distinction based on wave height and wave period between these different waves. More parameters that you can derive. So this is the maximum crest height as a function of steepness, skewness, excess kurtosis, all the things you can calculate from the wave data. There's very little to indicate that you can distinguish rogue waves from normal rogue Cs, or those records that contain a rogue wave from normal Cs. There's some indication that kurtosis might help, but not very much. In fact, if you look at the marginal distribution, you can't really tell whether the rogues, which is the dashed, is different from the normal Cs. So these are all things people have thought you might be able to say something about rogue waves from the measurements that we can make at sea, and whether we can really understand rogue waves based on these sorts of things. The final thing we looked at were spectral width parameters. We measure your wave spectrum. The narrower it is, the more likely that the waves are near a single frequency. That's very unusual in the ocean. We have two spectral parameters. Oops, sorry, did that press the wrong button? We have two spectral width parameters that we use. Epsilon and nu, these go back to the 1950s, when all this theory was thought about. The trouble with epsilon is it depends on the fourth moment of the spectrum, and there's evidence that the spectral decay at high frequency is f to the -5. So if you multiply by f to the 4, you get an f to the -1 integrate log f. That doesn't converge if you try and, you have to add a cutoff, which obviously we do in the measurements because the buoy has a cutoff. We don't measure waves that are shorter than a meter, basically, because of the size of the buoy. We tend to, I'm not very convinced about this part of the answer, so I'm not going to talk about that. But there is some evidence that from this parameter, which is perfectly stable as a spectral parameter because it only goes up to the second moment of the spectrum, there is some evidence that both for crest or H criteria, that the rogue seas are broader. So there's a more frequency spread in the spectrum than they are for normal seas. So broader seas might have more rogue waves. How am I doing for time? I'm probably ahead of time. I'm just going to get myself a glass of water. Excuse me a minute. So the next thing we had a look at was the wave shape. There's these sort of anecdotal stories of the ships falling into holes in the ocean or hitting a wall of water. And we calculated the shapes. This is scaled by the peak period, which is possibly not the best way to do. We tried it a different way. I won't go into too many details. But basically, the rogue waves are the blue curve. This is with the criterion that the rogue wave height is twice the significant wave height or bigger than twice the significant wave. We also have rogue waves with the crest height is greater than 1.25, the significant wave height, and the highest 1% non-rogue waves. And as you can see, the non-rogue waves don't have as big crests or as deeper trough. The rogue waves based on the wave height have this deep trough preceding the crest, and the ones based on the crest height tend to have a much peakier crest, but not such a deep trough. There are problems with this analysis because scaling by the peak period means that the crests and troughs for different seas don't necessarily align in the same way. So you're averaging lots of things out. We tried a different scaling based on individual wave, calculating the period of the individual waves, and then you can look at waves with HOHS 2, 3, 4, etc., and get the different wave shapes. Sorry. Do you have any spatial distribution? Spatial distribution. I'll talk about something about that in a minute. No, it's a time measurement. There's no spatial information in there at all. We have zero spatial information. Well, this is the hole. So, I mean, if you're sitting on a ship and you have the waves coming towards you, you will go down that hole. That's a hole. I mean, in turn temporarily, but it'll also be obviously a hole spatially. Sure. What do you mean long or short waves? These are all, most of them are not, I think it's only the 10-meter depth buoy that might be feeling the bottom. All the other ones are in water. So if you have a 100-meter wave, as long as you're in deeper than a quarter of the wavelength, so 25 meters, you're in deep water for all practical purposes. You don't need to worry about the bottom. So most of these are deep water waves, so the bottom doesn't play a role, except possibly for the buoy that's in 10 meters. I haven't looked at that very closely, so I can't remember offhand. It depends on the wavelength to depth ratio. But most of these are deep water waves, they're not shallow water waves. So the bottom is largely irrelevant in our analysis. We didn't bother to look at that in any detail. Like I say, it might play a role in the 10-meter depth water, but it's not really not very important, I don't think. Anyway, so that was wave shapes. And now we're looking, this is a plot, which I always find difficult to understand, so I'm not sure I'm going to explain it very well. Rather than looking at individual wave heights for rogue wave, this is looking at the seas, the 20-minute records in which the waves occur. So we are looking at the logged significant wave height and the logged zero crossing period, a function of the logged percentage of rogue Cs for each of the 80 buoys. So each dot on this plot is one of the buoys that we have. And you can see that as the logged wave height goes up and logged wave period goes up, the percentage of rogue Cs will go, I always get this plot the wrong way around, go down. Which is sort of, I think it's a typical power law behavior. Rare events are less frequent when mean HS and TZ increase. So I don't think there's anything too surprising about that. But what's interesting here is what we did find, and explains that double peak structure in the period marginal distribution that I showed you earlier, is that, if I remember which way around it is, the circles are for the Atlantic and the squares are for the Pacific. And there's different period distributions in the Atlantic and the Pacific for our observations. And the reason for that is quite simple. We're at mid-latitudes, the winds blow from west to east. That means that if you're on the west coast of the USA, the wavelengths will be longer because there's a longer fetch for the wind to blow across, so the waves will develop further, so they'll have longer periods. And if you're on the east coast of the USA, the winds are blowing from west to east, the waves don't have as much time to develop, so you'd expect shorter period waves in the Atlantic, which is indeed what we're seeing here. So that sort of completes my discussion of the sort of gross parameters, HS, TZ, all these other things that we might have wanted to get some handle on this. The only thing that showed up that was interesting was the spectral width parameter, suggested that that mattered. Let's talk about trends. Now, for trends, we decided that you needed at least 10 years of observations to at least even attempt to do a trend. Whether that's good enough is debatable, but that's, you know, given the observations we have, that's the best we could do. So our 80 buoys were subsetted to 15 used in the trend analysis. The yellow dots is where the buoys are. The oil platforms here on the little purple hexagons. And then there's ports also along the coast, west coast of the USA, which are marked in terms of little triangles. So this is an area which does suffer from problems with rogue waves. And so we were looking at rogue waves in this area, looking at trends. The period that we have data for is 94 to 2016. Not all of them for that length of time. Some of them are for shorter times. But that's basically the data we analyzed. Abnormality index is just the height of the rogue relative to the background significant wave height, and the excess is just taking 2 from that to normalize it in some way. So one of the things we did was seasonal variations, so we analyzed the data seasonally. I don't want to bore you with a lot of details, but there's seasonal occurrence, height of the wave, this excess in abnormality index, and the bandwidth parameter new that we looked at. And these are the various locations of the buoys. And as you can see, there's considerable variability, but the message to take away from this is, rather than looking at any particular point and thinking about it, is that in some places seasonality matters, in other places seasonality doesn't seem to matter. But you can't assume that if you're making some sort of statistical inference about rogue waves that you can ignore seasonality. You need to think about seasonal effects, and you need a lot of data to do that in any sensible fashion. So these are trends percent per year changes in 3 parameters: the mean significant wave height, the 90th percentile significant wave height, and 99th percentile significant wave height. We did this because there have been some satellite-based results on significant wave height from Young et al. In Science, and we get more or less similar results to them. We do see changes in the 99th percentile that are significant. The little blob at the top is telling you the significance level. Don't want to go into this in too much detail. This little bit is blown up here so you can see the details. So the buoys down here are in this blown up part. But as you can see, there's no real consistent pattern. Possibly along here, there's some consistency in the 99th percentile, but we did get similar results to Young et al. For this part of the world. They were doing it from satellite data. We then went on to look at trends in rogue waves. not any clear pattern, I would say. I can't work a clear pattern. There's some interesting things, like in a few locations, rogue waves are getting more rogue. So this abnormality index is increasing. There are a few places where that's happening, which is the blue line here. Those two are significant. This one's probably not significant. Significance, tricky to be absolutely confident about what's going on. There's some places where the rogue wave occurrence is decreasing. No clear pattern that we could determine. So I just wanted to mention a paper that's just come out this year, which I think is quite interesting, and I've not really had time to get to grips with it. But going back to this problem of, can you derive information from standard wave products? Gennady and Chikon in Nature Science Review Reports just this year, they have produced a paper. The initial analysis was done on 0.9 meter wavebuoy just for over a year's worth, maybe under a year's worth of data in 45 meter depth water. They analyzed the data same way we did 20-minute seas. And then they used 11 years of data from 6 meter nomads, so that much bigger buoys, and 3 meter discus buoys further offshore. And they have this link between the correlation, crest to trough correlation, which they calculate from the spectrum, and the probability. So they get a remarkably good fit, and H max, H rogue, as we would call it, over HS as a function of R as well. They've got some good statistics. Their wave records are much shorter than ours. I would have some questions about using such large buoys to come to any conclusion, because I think there's issues about what you're actually measuring with large buoys. But it's an interesting paper, and I think this is would have been an interesting thing to try on our data set. I didn't think of it, so otherwise I'd have done it. So these are my conclusions from our study. The rogue waves can't be characterized in terms of standard sea state parameters, at least not by the ones we examined. It's possible that Gennady and Chikon have got something there in their work. Spectral bandwidth appears to be related to rogue wave occurrence. So this broader bandwidth might be, because we're only working in one dimension, it might be an indication that there are multiple wave regimes. So you get different waves from different storms crossing, and that would lead to a broader bandwidth, because it would have they would have different frequency distributions. I didn't say I'd say anything very much about theory, but broad spectrum suggests Benjamin fear instability is an unlikely mechanism, because that assumes that your waves are basically traveling in one direction, and that seems unlikely. And there are significant spatial, when I say spatial region, I mean regional rather than spatial on a patch of the ocean, seasonal and interannual variations in occurrence. They're more prevalent in lower HS and shorter TZ seas, which in a way is a good thing for operators, because smaller wave height means that the rogue waves will be smaller if they do occur. And any predictions of rogue wave occurrence need to be regionally specific. And then my outstanding questions. There are effects of directionality. I think there's a really interesting paper by experimental paper by McAllister et al. I did some calculations way back in the 1980s on breaking waves. If you set off a unidirectional wave train and it breaks at quite a low height. I also did some calculations, which I never published, of partial standing waves and standing waves, where you send two wave trains towards each other. There is no wave height restriction in those circumstances. You can get these huge jets going upwards. And that's what McAllister et al. Found in their paper. I think if they set their two wave systems off at about, I think it's about 120-degree angle, you can get quite very large sort of upwards motion, which I think is jet-like, and I think that's a partial standing wave effect. And had we downloaded the directional data for our buoys, we could probably have looked at that, but we didn't do that, unfortunately. So I think you may be able to do something about rogue wave occurrence, not with the parameters we looked at, but maybe by including directionality or that correlation, crest-trough correlation parameter that Meric and Chikon have just come up. And then there is the area that somebody asked me about, spatial statistics, a whole. Can you actually determine spatiotemporal statistics of rogue waves over an area? And there are people doing experiments off towers with stereo cameras, but they're all fairly small scale. Luigi Cavalieri is one of those people doing things like that in his group. I think off the Tower of Venice in the Adriatic. So there's some interesting questions left. I'll stop there. Thank you.
Thank you very much.
Wait for the mic. And then the people online can hear you. It's okay in the room, but it's the online people who can't hear.
Right. Now, I'm sure you're aware of the ECMWF model.
Yes.
Where they're claiming that they can give a probabilistic model for somebody trying to cross the North Atlantic. And you didn't mention it. I was wondering if you think,
okay, so
what were your thoughts?
That would be my friend Peter Janssen of long standing. So I think they calculate the Benjamin Fear Instability Index. The thing is that assumes that the mechanism is a Benjamin Fear instability mechanism, which I do not believe. As an observational oceanographer, I do not believe you get Benjamin Fear instability in the ocean. Maybe on very rare occasions, but it's not. If you have broadband spectra, it's never going to work. There's a mechanism in the ocean. You've got crossing sea. The more common, if you look at any wave data, sorry, I'm probably standing in front of the camera. If you look at any wave data, there's often crossing seas. There's different frequencies because they're generated by different storms. Benjamin Fear works beautifully if you've got a nice narrow wave tank where you send all the waves down within one tank and instability happens, modulation and stability and things go.
So your replacement of Benjamin Fear would be, so your replacement of a Benjamin Fear mechanism would be a crossing sea states mechanism?
I quite like what McAllister et al. Have done in the tank. And I think if you could generalize that, so we get, a spectrum like Peter Janssen calculates and will give you directional information. The question is, can you turn that into something that will give you a predictive ability in the real world? And I can't remember from McAllister, I don't think they discussed that because they got this rather fancy wave tank where they do the experiments. But in principle, if you could do that, or with the correlation one that Gemrich and Chikon, you can calculate that correlation from a spectrum. The point is that the wave modeling is all done spectrally. So it doesn't tell you anything about the surface because it's a spectrum and they don't preserve the phase information in the spectrum the way that wave models work. So you can't really say much about the surface as a real, as a two-dimensional measurement of height. So it's got to come from the spectrum, and that restricts what you can do. And I certainly don't think, I would disagree with Peter. I don't think Benjamin Fear is significant for the real world, personally.
Nicola?
Thank you. My question maybe is connected to your last point. So you have so many data points and your boards are not so distant one from the other. Can you measure correlations, saying so, for instance,
they're too far apart. I mean, they're kilometers apart. So, if you think about waves are typical waves, 100, 150 meters. You need to be pretty close to do spatial correlations. If your boys are 10 kilometers apart, I wouldn't believe anything very much.
So it means if a rogue wave occurred here at time t, there is no correlation 10 kilometers away, or there is no enhanced probability to see something, not direct, not the same one, but a enhanced probability.
Okay, so well, there's two things. One is you would have to have the buoys in such a way that the waves were traveling from one buoy to the next.
Well, maybe it's not the same way, but you're in a region where they are likely to occur.
You need to have some communication of information, surely.
Okay, you're the expert, but maybe you may say in this area at time t in this zone there is an increased probability, and maybe this could reflect.
I wouldn't like to say how spatially. I mean, I just don't think that 10 kilometers away they're going to be that correlated. I mean, I haven't tried that, so I can't answer you definitely. But
maybe
it's probably worth looking at.
That's already an information then. The fact that
my gut feeling, based on what we've done with wave statistics, is that they wouldn't be that correlated 10 kilometers apart. Okay. But I could be wrong, and we haven't looked at that, so I don't know.
There is an online question. Can rogue waves create eddies?
What, in terms of the sort of thing that Emma was talking about? No. Well,
correlated to thoughts.
Yeah.
I don't think I think the eddy it's more complicated. They can't create them. They can be influenced by eddies. Certainly, we have examples of wave propagation across eddies where the currents can focus the waves or disperse the waves because of the way the currents are. But that's a sort of wave current interaction problem. Just like on the Agulhas, which she mentioned, which is a very strong current off Africa. they lost many tankers because the tankers, captains of the tankers like to go in the Agulhas current because they have an extra 2 meters per second in terms of ship transit time down the east coast of Africa, which is great in terms of saving fuel. But unfortunately, you get big waves coming up from the Southern Ocean onto the current, and waves onto current steepen and break. So they lost a few super tankers, bent a few super tankers doing that, so they stopped doing it. They tend not to travel in the current now for that reason. That's a wave current interaction rather than, we're not really looking at wave current interactions.
Did you kind of enter this study with any sort of assumptions on statistical equilibrium in your analysis? What, if yes or no, what are your findings tell you related to thinking about statistics of rogue waves in any sort of?
Well, I guess my starting point is that basically most things in the ocean in terms of waves are basically Gaussian statistically, and can be characterized by a few typical parameters for most circumstances, but there's non-linearity as well, because wave breaking is, for example, non-linear. We don't really capture that in spectral models. That's sort of parameterized in wave spectral models. It's very difficult to measure in the open ocean. I've tried to do some work on that. We built a special buoy to try and measure wave breaking. It's really difficult to do in the open ocean. So yes, I am making some underlying assumptions that basically my statistics are more or less the same everywhere. That's possibly not true, but you know, what else can I do? I mean, I haven't got any alternative ways of doing it.
Well, but do your findings support that assumption? Is there any sort of internal competition there? Because you seem to suggest on your previous slide, your main conclusions.
I can't remember what I said then.
Right, you can't characterize rogue waves in terms of standard sea state parameters. At least not by the ones you examined. So
well, these are ones that come out of, I mean, basically those parameters come out of a Gaussian theory of waves. So yes, there may be other non-linear, well, I mean, that's what the Benjamin Fear index is that the gentleman mentioned earlier, sort of the non-linearity type parameters, but I haven't found any evidence that but we haven't, I guess skewness is the only parameter that we've, not skewness, well, skewness is one, but also kurtosis, but also steepness will be the big sort of like parameter for non-linearity. We didn't find any strong dependence on any of those parameters. So Gaussian statistics seem pretty good for most things, but not for rogue waves, because I think my feeling on rogue waves is there's and essentially you've got a Gaussian sea, and then things interact and non-linearity kicks in when things get steep enough. But most of the time, and if you look over the side of a ship, the waves sort of have peakier crests and flatter troughs. So non-linearity clearly in there somewhere, but characterizing that steepness didn't seem to do it for this study. There may be other parameters you can use. I think I'm basically view the ocean as largely Gaussian in terms of waves, with a bit of non-linearity, which explains the rogue waves and a few other things like breaking. So I don't know if that helps. That's my view.
So is it possible to find a rogue wave in a linear sea?
Well, I guess theoretically.
Microphone while you're thinking.
Well, I guess
Is it impossible to find a rogue wave in a linear sea?
Well, in the linear sea, in the sense of it's purely theoretically a Gaussian. If you set up a numerical model with just Gaussian statistics, then you would get big waves because Gaussian has got long tails, so you will get big waves. I mean, I'm not sure rogue waves as we think of them are purely just the tail of the Gaussian distribution type thing, or the tail of the Rayleigh distribution, if you think in terms of.
So there's different types of rogue waves.
No, I just. Oh, they define a rogue wave in a clear. Yeah. Well, I'm using it as it's been traditionally defined. I didn't think up the definition.
An agreed concept then.
Yes, it's an agreed concept. No, but if you go back to that plot where I had the different lines as a function of HS height, it's not clear where you would, you know, somebody was saying, I can't remember who said to me, somebody said to me that 2.7 is the current thinking on rogue waves. Well, if you have 2.7 HS, you're going to find hardly any rogue waves at all in our data set. That is an arbitrary definition. I mean, there isn't. I can't remember. I think Gennady, that paper I mentioned, they might use 2.2 rather than 2. I can't remember. But different authors use different definitions anyway. So, as an observation, you have to do the best you can with the data you've got.
Sorry, Can I ask a question? We've seen this image of Drapner wave many times during this conference, but I don't think we learned two essential characteristics for anyone who studies the wave. So perhaps you could help us and say, what is the fluid depth at this place where this was measured? And what is the wavelength of the Drapner wave?
I have to go in and look that up. I can't remember off the top of my head. I think you'll find it's in the southern North Sea, so it's probably sorry. Sorry, let's go back. If it goes back far enough. Did I miss my Drapner wave? Oh. 5, 6, 7, 8. It's about 8 peaks in there in 100 seconds. So that means it's probably about a 12-second wave. 12-second wave will be, just think off the top of my head, no, 150 meters. I might have got that wrong. It'll be right, that sort of number. Water depth in the southern North Sea, depends where you are, might be 30 meters. So it's probably marginally, it's a long wave in shallowish, but not, I don't, you know, the bottom's probably not important. If it's 120, if it's 150 meters and it's 30 meters water depth, well, it might matter. I'm not sure it does really. I mean, if it was like 130 meters or sorry, 150 meters in 10 meters, then yes.
Is it possible to find this in the literature? I don't know.
I'm sure it must be. I don't know.
Yeah.
I have read a lot of road wave papers. I'm sure it's in there somewhere. I can't remember what.
Thank
I mean, you know, I can look that up and let you know afterwards if you give me your email or something. I'll send you the information.
No questions?
Is there any evidence that Stokes waves exist in the ocean?
Oh yeah. Well, I mean, it depends what you mean by Stokes wave. If you think like second order theory shows that you have a peakier crest and a flatter trough.
Traveling waves, just like of almost the same shape, or they always modulated?
No, because if you look over the side of a ship, I've been to sea a lot. If you look over the side of the ship, your immediate impression is that the waves have peakier crests and flatter troughs. But the other impression you have is the waves are traveling in all sorts of directions. So you've got a very confused sea. You haven't got this nice, uniform, two-dimensional, long crested wave just going past you. That's very unusual. Most of the time, you've got waves going in all directions, but on the whole, the crests are peakier and the troughs are flatter. So yes, I believe non-linearity exists in the ocean. That's no problem. Stokes wave, if you mean a nicely propagating without change of shape wave, probably not.
You short crest Stokes waves.
Well, they're not really Stokes waves then, are they? Because that's not the theory that Stokes did in 1887. So it's not really a Stokes wave. Stokes' theory was just unidirectional waves, not so.
So I have a quick question. This might be a needle in a haystack question, I guess. But in those observations you had with the buoys, were there any cases where you were able to capture a rogue wave? Were you also able to capture data from some other sensor source? And the reason I'm thinking about this is I think on your map, there were some near Duck, North Carolina. And I know they have, for example, pressure arrays. But again, needle in a haystack.
To be honest, it took us a long, well, I say took us, I'm using it in the royal sense. My students, it took my students a long time to download quality control and just put together this data set before we even got started. So to be honest, we didn't go and look for anything else because I wanted him to get on and do his PhD rather than spend his time chasing around looking for more data or different types of data. We wanted to be consistent. So, you know, that's why we stuck with these particular buoys. I think that was more important than anything else at the time.
Okay, let's thank our speaker again. 15-minute break. So we have just 15-minute break, 1:45. We are back for the last talk and then we have discussion. Okay.